Hello students of class 2. Today we will be starting with a new chapter, and it's from inorganic section and it's coordination compounds. So these coordination compounds are a new type of compounds that you are going to learn today. Okay, so please pay attention. Coordination compounds are those molecular or addition compounds in which a central metal atom or ion is permanently attached to certain atoms or groups of atoms which are known as what? Ligands. Okay, so from the definition, you might not understand it well, but if I give you some example, then you better understand it. Okay, so see, for example, potassium ferrocyanide. So this is a coordination compound, or you can also call it as what? Coordination complex. So here, this CN6, which is inside this bracket, this CN is called as what? Ligands. Now, these ligands are directly coordinated with central metal atom. This Fe is the central metal atom that this definition tells about. Okay? So this Cn is the ligand, this Fe is the central metal atom. Now, here in complexes, the metal ion is usually from transition series. That is after calcium. You have those 10 these groups, those are known as what? Transition metals. And in a complex, you always find this metal to be a transition metal. Now let's discuss in more detail. Now see, here you also know about the double salts, like more salts. More salts. It is the formula for more salt is what? Potassium sulfate, ammonium sulfate, and 6 molecules of water. It is ferrous sulfate. So the formula for more salt is ferrous sulfate, ammonium sulfate, and it is associated with 6 molecules of crystallization of water. So this also looks like a coordination compound, but actually it is not. So today we are going to learn about the differences between this more salt, which is a double salt. Okay, it is a double salt. Now, whenever it is dissolved in water, so whenever this double salt, here we have taken particularly more salt, whenever it is dissolved in water, what will happen? They will dissociate into its respective ions. So you will be having Fe2 plus ion plus you will be having sulfate ion, 2 minus plus you will be having ammonium ion. Okay, so once it is dissolved in water, this double salt, more salt is dissolved in water, they will give you the test for ferrous ion, sulfate ion, and ammonium ion. This says that they get completely dissociated in water. Now let's talk about coordination complex or coordination compound. Now, whenever you have this coordination compound, therefore FeCN whole 6. This is potassium ferrocyanide. Whenever it is dissolved in water, it dissociates into K plus 4 atoms of K plus. Then you have FeCN whole 6. Now here you have to understand it very properly. Look over here. Here, whenever this is a coordination compound, whenever coordination compounds are dissolved in water, it ionizes as this K plus ion, and this FeCN4 part will be attached to it. And here it will be having 4 negative, that means 4 negative charges. Now here what you have to see, you have to know that this, whatever is inside this bigger bracket here, this will never dissociate. This will stay as it is, even after dissolving in water. So here you won't be getting the test for ferrous ion and cyanide ion, because its property, whenever it is staying as this complex, its property is different from ferrous and cyanide. Therefore, here you will not give, it will not give you no test for Fe2 plus ion or and Cn minus ion. So this is the difference. Okay. So in double salts, all of them, they will be dissociated into individual ion, and they will give you the test for each ion. But in case of coordination complex or coordination compound, whatever is inside the bigger bracket, this big bracket, it will stay as it is. It doesn't dissociate. Therefore, it won't give test for what? Here, this F is not free. It is not present as Fe2 plus ion. Therefore, it doesn't give test for ferrous ion and cyanide ion. Now, let's discuss about some important topics of coordination compounds. Now, here, if you take important terms, okay, now we will be discussing about important terms. So let's take this part, FeCN4 4 minus, this is the complex part. Okay. Now here, this is known as I told you, central metal atom or ion, and this is known as what? Ligands. Okay, and here this is known as ligands. And one more thing you have to know, as we have taken this complex K4 FeCN6. Here, this part, which is present inside the bigger bracket, this part is known as what? Coordination. It is known as coordination sphere. This is known as coordination sphere. Now, these ions, either cation or an ion, if it is present which is outside this bigger bracket, then that is known as what? That is known as ionic sphere. It has come to balance. It has this ions, which is, it could be positive or it could be negative. They are attached to this complex just to maintain the electrical neutrality. Okay, and you have to remember this is what? This is the coordination sphere. Now let's discuss about coordination number. Now, coordination number here in this case is what? It's the number of these ligands which are directly coordinated with the central metal ion. Therefore, what is the number of ligands in this case? It is 6. Therefore, its coordination number is 6. That is the coordination number of ion Fe2 plus in this complex is 6. Now let's discuss about oxidation number or oxidation state. So let's take this example. Now in this case, if you want to know the oxidation state of Fe2 plus, here it is not given as 2 plus, but you have to know it. Okay? How will you calculate it? For that, what you have to do is, you need to consider it as X. Now here, potassium, you know the valency or the valency of this, each potassium is positive 1. How many of them are there? 4, and the valency of Cn minus or the electrical charge carried over Cn minus is what? Cn is what? It is minus 1. So how many of them are there? 6. So now in this way you can make this equation and calculate the value of x. So let me take one particular example. Like here we have copper NS2 whole 4, and you have sulfate ion. Okay, copper. Here in this particular contents, you do not know the oxidation state of what? Copper. So let's consider it to be X. You know ammonia. Ammonia has lone pair and it coordinates to the copper atom through its lone pair. Now whenever lone pair is involved in this coordination with the central metal atom or ion, then its electrical charge is 0. And sulfate, you know the valence of sulfate is minus 2. Yes or no? So here, in this case, you can easily calculate what is the oxidation state of this copper. So X plus, here 4 molecules are there, but the charge of each NS3 is what? 0. It is a neutral ligand. And here we have what? This is plus, you have minus 2. And how many of sulfate atoms are there? 1 equals to 0. Because as a whole, this is a neutral molecule. Now you can easily get the value of this plus X. Here in this case, what we have to know is this is minus 2, this is 0, 4 into 0 is 0, plus this is minus 2 equals to 0. Therefore, the oxidation state of copper is plus 2 in this complex. Okay? So, hope this is, you have more examples in your book. You can try with other examples. Now, let's take this complex. If you want to know, say you have copper NS3 whole 4. So this I have already explained. Okay? So there are more examples in your book. You can try with them. Now to calculate the oxidation state. Now let's discuss about classification of ligands. So classification of ligands, we are going to discuss about classification of ligands. Now it can be classified into two different categories. First is classification on the basis of charge. The first one is classification on the basis of charge. So, on the basis of charge present, ligands will be classified into three categories. That is neutral ligand, B anionic ligands, and C cation ligands. Now neutral ligands, you know, that means they do not, whenever they are coordinating with central metal ion, central metal atom or ion, they do not give any charge. That means mostly they usually have presence of a lone pair or two. For example, as we have discussed just now, ammonia, you have ammonia, water molecule, etc. This contains lone pair, or these are donated, but it doesn't give any negative charge to the net negative charge to the central metal atom. Now anionic ligands, as the name suggests, they have negative charge, and this negative charge are donated to the central metal atom. Now for this you have example as you saw just now, Cn minus, cyanide. Yes or no? You have Cn minus, you have halides. X minus means it will be F fluoride, anion, chloride, bromide, or iodide. Okay? Now cation ligands are those ligands which are positively charged and they are responsible for coordinating with the central metal atom with its positive charge. That means they possess positive charge, and whenever they are coordinating with the central metal atom, then they donate its positive charge. For example, you have NO, or hydrogen, that is NH2, here NH3. Whenever it has a positive charge, this also has a positive charge. This is known as hydrazinium. So these are the classification based on charge present on the ligands: neutral, anion, and cation. As the name suggests, neutral, no charges; anion, they have net negative charge; cation ligands, they have net positive charge. Now let's discuss classification of ligands on the basis of number of donor atoms. On the basis of this is number 2 now. Okay, so here classification is based on number of, on the basis of number of donor atoms. Now, on the basis of number of donor atoms, it can further be classified into various categories. Number 1 is monodentate ligand or unidentate ligand. It also has a name, unidentate ligand. Okay. Now, as the name suggests, monodentate or uni, it means what? It has only one coordinating site, or it forms coordination bond with the central metal ion through only one atom. Okay? For example, you have just now you have discussed about this oxygen present here with water. It donates to only one site as ammonia. And other examples, Cl minus, etc. So they have only one side by which it donates its electron to the central metal atom and gets coordinated. Now number 2 is bidentate or didentate ligands. Now bi-di. So it's it is clear from its name itself, it has two coordinating sites. Now in one single ligand is present, but it can form bond from two different atoms present in it to the central metal ion. For example, you have this ethylene CH2, ethylene diamine CH2, NH2. Now it has two sides. This lone pair is present, this lone pair is present. Now this can also be used in forming coordination bond with the central metal ion, and this lone pair can also be used in forming coordination bond with the central metal ion. Another example is you have oxalator, that is CH2, you have COO minus and COO minus. That is COO minus, COO minus. Here again, it has two coordinating sites and it can be donated to the metal atom. Therefore, it is known as what? Bidentate or didentate ligand. And the name of this compound is ethylene diamine. Ethylene diamine. Okay, and this is oxalate 2. Here in coordination compound, and then you have to write it as O. Oxalate, actually it is oxalate, but here in case of ligands for coordination compound it is oxalate. Okay, so these things you have to remember. Now let's discuss about tridentate ligand. So we are going to discuss about tridentate ligand, that is C. Tridentate ligand. Now as the name itself suggests, tri means it has 3 coordinating sites. It means it can form, this ligand can form bond with the central metal ion to 3 different groups. That is, here you can see in this example, ethylene diamine. This is diamine. Diamine means it is didentate ligand. Now whenever this one hydrogen of NH2 is replaced with again CH2 group, and here if you have NH2 group, then it has 3 donating sites. Means it is an example of tridentate ligand. And the name of this compound is diethylene triamine. This is ethylene part, this is ethylene part, therefore diethylene, and here you have what? 2 NH2 group, therefore 1, 2 and 3 in fact, therefore this triamine. Okay, so the example of this tridentate ligand is this diethylene triamine. Similarly, let's discuss about tetradentate ligand. Tetradentate ligand. Now, in this tetradentate ligand, you have 4 coordinating sites. This tetra means what? It has to have 4 coordinating sites. Now, you can again get tetradentate ligand from this particular tridentate ligand itself. So, you need to extend one more, this NH2 group. So we have CH and CH here, CH2. Now this was NH2, NH, and here we have CH2. Now this, here you have what? NH2. Now one of the hydrogen of NH2 will be again substituted with CH2 and NH2. Now in this way, you get how many coordinating sites? 1, 2, 3 and 4. So this is the example of tetradentate ligand, and you can name it. This is 1 ethylene, 2, 3. Therefore it is triethylene. And how many NH2 groups are there? 1, 2, 3 and 4. Tetraamine. Okay, the name of this ligand is triethylene tetraamine. Now similarly, let's discuss about pentadentate ligand. This is E. Pentadentate ligand. Now again, as the name suggests, it has 5 coordinating sites. Therefore, here you can take an example where it has 5 coordinating sites. Here in this case, you have this group CS2, CS2, and here NH. Now, here instead of NH2 group present, there would be COO minus group. This and this side also you have what? This side also you have N group here. Now this is attached to COO minus, and this is also attached to COO minus. Means 1, 2 coordinating side, 3 coordinating side, 4 and 5. So 1, 2, 3, 4 and 5. Therefore, it is known as what? It is also known as pentadentate ligand. And the name of this compound is ethyl diamine triacetate. Ethyl diamine and how many acetate group is present? 3. Therefore, it is triacetate. Triacetate. The next ligand is hexadentate ligand. Hexadentate ligand. Now in this you have what? 6 coordinating sides. Now here, instead of this hydrogen, you can have COO minus group, and that would be the example of what? That would be the example of hexadentate ligand. So let me write and COO minus. Here you have COO minus CS2, and here you have COO minus and COO minus. So 1 coordinating side, 2, 3, 4, 5 and 6. Therefore, this is the example of hexadentate ligand, and its short name is EDTA. Okay? That is ethyl diamine tetraacetate. So here, the difference between this and this is what? Here instead of hydrogen, what is present? COO minus. Therefore, 1, 2, 3, 4, triacetate. Okay? So these are the main classifications of ligands on the basis of donor atoms. Now one more category is there, that is chelating ligand. Okay? Now chelating ligands are polydentate ligands, means they have more than one coordinating site. They have what? More than one coordinating site. So we are going to discuss about chelating, chelating chelating ligands. Now, these chelating ligands are what? They are polydentate, means they have more than one coordinating atom present in it. Okay? More than one coordinating atom present in it. For example, you have didentate ligand, tridentate ligand. These are all what? Polydentate ligands. So ethyl diamine, the simplest example, CS2, you have NH2 group, and no lone pair is present here. You have NH2 group present here. Okay? So whenever this coordinating sites of this polydentate ligand, whenever it is coordinating with the metal, and if it is forming a 5-membered or 6-membered ring, okay, then they are usually very stable. And these ligands, if they are involved, and if it is forming a 5-membered or a 6-membered ring with a central metal, atom or ion, then those ligands would be known as what? Chelating ligands. So if you have metal, suppose it's a central metal atom, and this ligand is involved, that means CS2 is present. Here you have NH2 group. Here also you have what? NH2 group. So whenever it is coordinating, it is NH2 donates its lone pair to the central metal atom. Similarly here, this NH2, whenever it forms a coordinated bond with this metal atom, then you can see that it forms a 1, 2, 3, 4, 5 member ring. And such ligands, such categories of ligands are known as what? These are known as chelating ligands. Now these chelating ligands, it usually forms 5 member ring and 6 member ring. Okay, whenever it forms a coordination complex with the central metal atom. And as I told you, these complexes are more stable compared to other complexes where we would have chelation. So with this we come to the end of this today's class. So in the next class we will be discussing more about coordination compound. Till then, take care. Thank you.